we're going to look at the ALEKS problem from homework 7 using an integrated rate law for a first order reaction. And I feel like this problem is going to be pretty straightforward for you because you are just plugging stuff into the first order reaction or first order integrated rate law. So let's start by just kind of reminding ourselves what the form of that is. It's the natural log of our reactant at whatever time we're talking about minus the rate constant K times time plus the natural log of our initial concentration of A. And so let's see what kind of variables we have here. We've got a rate constant, so there's our K. It tells us that a vessel contains that stuff at a concentration of 0.44, so that's going to be our initial amount. Calculate the concentration, so this is what we're trying to figure out. We don't know what the A is at particular time at 2.4 seconds later. So that's our T, 2.4 seconds. And so all we have to do is just plug this stuff into this equation. The rate constant, 0.369, just make sure you don't lose that negative sign in the equation. And our time, 2.4, and I'm double checking to make sure that we are dealing with the same time unit so that we can multiply those without any problems. And the natural log of the initial concentration, 0.440, that's it. Oh, yeah, well, let's go through because we have to undo the natural log, which sometimes is kind of tricky. So negative 0.369 times 2.40 plus the natural log of 0.44, and that's going to give us the natural log of A at time T is negative 1.7066. And to get rid of the natural log to solve this equation, we are going to use the e to the x function, e to the negative 1.7066. That will undo the natural log, and the concentration that we end up with is 0.18 molar. So that's pretty simple. And the other ALEKS problem that we have that you're ready for is calculating the change in concentration after a whole number of half-lives for a first order reaction. So this is not a problem that you can solve using your first order half-life equation. And let's talk about why. So for a first order reaction, the half-life equation, T1 half, is what you have is 0.693 over K. So first of all, the problem is asking for you to calculate a concentration, which isn't even a variable in this equation. Like, that's not even a thing here. And then second of all, in order to use this equation, we need to know K, the rate constant, and that's not a number that's given to us in this problem. So if you're trying to use this equation right here, you're going to be sad because this is not the correct equation to use for this equation. You would use that equation only when it was saying something like, what is the half-life of a particular reaction? So instead, this problem is actually really, really simple. It's telling us that we have first order reaction with a half-life of 20 minutes. That means every 20 minutes, the concentration is going to decrease by 1/2. It tells us that we have 0.1 microgram per milliliter of some kind of drug. And the question wants to know, what will the concentration be in 40 minutes? 40 minutes is an even, what's the word I'm looking for? It's an even accurate, no, it's a good number of half-lives. It's 2 half-lives of this guy is going to be 40 minutes. So it makes it really easy for us to work with. So this is our initial amount. And then after 20 minutes, which is 1 half-life, after one half-life goes by, that initial amount is going to be cut in half. So 0.1 divided by 2, 1/2 of 0.1, that's what we have. And then after we do another 20 minutes, so this is going to be after a total of 40 minutes, and this is going to be a total of 2 half-lives that have passed, we're going to cut that in half again, and this is now going to be 0.025 micrograms per milliliter. So for every half-life, we're decreasing the concentration in half. And you do have to do it incrementally like that. You can't just like find some way to rapid shot it. So let's try another one, just because some people get this concept really fast and other people don't. I like to not enter a 0 in front of my decimal place just to piss off ALEKS. So here we go for another one. In this one, we have a half-life of 56 minutes. Half-life of 56 minutes. We're starting with 1.1 micrograms per milliliter. So that's our initial amount. After our first half-life, we're going to decrease that in half. I'm going to actually use my calculator for this because I don't want to risk screwing it up. So 1.1 divided by 2, that's going to be 0.55 micrograms per milliliter. And that is going to be after one half-life, which is 56 minutes. And so now we're going to go again for another 56 minutes. Divide 0.55 by 2. That's going to give you 0.275 micrograms per milliliter. And after another 56 minutes, we're going to have 112 total minutes gone by. So we're not up to 224 yet. Let's go another 56 minutes. What's that going to be? 168 minutes. After 168 minutes go by, 0.275 divided by 2 again. That gives us 0.1375 micrograms per milliliter. But we are still not up to 224 minutes. So let's go for another half-life. After another 56 minutes, we're going to be at 224. So this is where we are trying to get to. We're going to divide in half again. 0.1375 divided in half one more time, 6875 micrograms per milliliter. To 2 sig figs, we're looking for 0.069.